Imagine running a company with hundreds of thousands of applications, like tiny little background tasks to massive data crunching operations. And all of them need to run flawlessly 24/7 across a global network of data centers. That's Google's reality. Boggles the mind just thinking about how they keep it all running smoothly.
It really is a massive undertaking. I mean, just orchestrating resources across tens of thousands of machines to meet those demands is an incredible feat of engineering.
And that's what we're diving into today. Borg, Google's secret weapon for managing this complexity.
Borg is Google's internal cluster management system. It's kind of like this invisible hand orchestrating this vast digital symphony for well over a decade.
So in this deep dive, we're going to uncover how Borg efficiently manages resources, handles failures, and maximizes performance across Google's massive infrastructure.
You know, one of the things that's so fascinating about Borg is how it manages to be both powerful and surprisingly user-friendly.
Yeah, that's one of the things that really intrigued me. It sounds incredibly complex, but developers don't actually need to be system experts to use it.
That's right. Imagine being able to submit your code and just telling the system, run this, please. Borg handles all the messy details like where it runs, how much CPU and memory it gets, and even restarts it if it crashes.
So it's all about simplifying the user experience.
Exactly. They interact with Borg through jobs and tasks using a special language called BCL. It's almost like writing a recipe for your computation. You tell Borg what you need, not how to do it.
So I'm curious about those details. How does Borg actually make those decisions about where to run things and how much resources to give them?
Well, that's where the Borg master comes in. Think of it as the brain of each Borg cell, which is just a group of machines managed as one unit.
So the Borg master is calling the shots, but if it fails, wouldn't everything just grind to a halt?
Not at all. That's the beauty of Borg's design. The Borg master is actually replicated for fault tolerance.
So even if one Borg master replica fails, the others keep the system running seamlessly.
Precisely. Which is why Google services like Search and Gmail are known for their reliability. Even if part of the system goes down, it doesn't impact users.
That's very reassuring to know. Now, here's something I found interesting while reading about Borg. The part that actually assigns tasks to machines, the scheduler, isn't part of the Borg master itself.
You're absolutely right. The Borg scheduler is a separate process. It's constantly analyzing pending tasks and looking for the ideal machine to run them on.
So it's like a matchmaking service for applications, constantly making sure everything is running in the right place.
That's a great way to put it. This separation actually enhances Borg's scalability. The Borg master can focus on the overall state of the cell, while the scheduler focuses on task assignments.
That makes sense. So let's talk more about this scheduler. How does it decide where a task should run?
It's a two-step process: feasibility checking and scoring. First, the scheduler checks if a machine meets the task's requirements and any constraints. Then, it scores each feasible machine based on a variety of factors.
So it's not just about finding a machine that can run the task, it's about finding the best machine for that specific task.
Exactly. For example, the scheduler tries to distribute tasks across different machines and even different physical racks to prevent correlated failures. If one machine goes down, you don't want all the related tasks to go down with it.
That's smart. It's like spreading your risk across multiple baskets.
Precisely. The scheduler also prioritizes minimizing disruptions, meaning it tries to avoid moving tasks unnecessarily. It'll factor in things like whether the machine already has the required software packages installed to avoid unnecessary data transfers.
So it's like a giant game of Tetris, trying to fit all the pieces together in the most efficient way possible. But what happens when there's just not enough room for a new task? Does it have to wait?
Well, that's where preemption comes in. If a high-priority task needs resources, Borg can actually kick out lower priority tasks to make space.
It sounds ruthless, but also incredibly efficient. So those lower priority tasks are just put on hold until resources become available again.
They're added back to the queue and rescheduled on a different machine. Borg's designed to handle these interruptions seamlessly. Tasks can be stopped and restarted without affecting their overall progress.
That's a relief. It's good to know that Borg has a plan for handling those high-stakes situations. This ability to dynamically adjust resources on the fly seems crucial for maximizing efficiency.
Absolutely. It's one of the key reasons why Google can achieve such high utilization of its infrastructure. They're not wasting resources on idle machines or over-provisioning just in case.
This all sounds incredibly complex. It makes me wonder how much overhead is involved in constantly monitoring and adjusting resource allocation.
It's surprisingly efficient. The Borg master calculates resource reservations for each task every few seconds, but these updates are communicated asynchronously, meaning they don't clog up the system. It's a very elegant solution.
Elegant indeed. And it's all happening behind the scenes, completely transparent to the users. They just submit their jobs, and Borg takes care of the rest.
Exactly. And what's particularly impressive is that Borg doesn't rely on fixed-size chunks of resources. Users can request exactly what they need, down to the millicore for CPU and bytes for memory.
That's amazing. It's like being able to buy ingredients by the gram instead of having to buy prepackaged boxes. It eliminates waste and allows for much more fine-grained control.
Exactly. That's another key factor in Borg's efficiency. It avoids over-provisioning, which is a common problem in systems that rely on fixed-size resource allocations.
So we've talked about how Borg efficiently allocates resources and handles tasks. But what about when multiple applications are running on the same machine? How does Borg prevent them from interfering with each other?
That's a crucial aspect of Borg's design. Imagine hundreds of different applications, all running on the same hardware. How do you keep them from stepping on each other's toes?
It's a great question. It seems like there would be a lot of potential for conflict and resource contention.
Absolutely. That's why Borg employs a multi-layered approach to isolation, ensuring that applications can't interfere with each other's performance or security. It's like having built-in safeguards to ensure fair play and prevent any application from becoming a noisy neighbor.
So it's not just about sharing resources, it's about sharing them safely and fairly.
Exactly. And Borg accomplishes this through a combination of techniques, starting with something called Root jails for security isolation.
Fruit jails, what are those?
Think of them as virtual sandboxes for each application. They restrict an application's access to only its own designated files and directories. It's like giving each application its own private workspace, preventing them from snooping around or messing with each other's files.
So it's kind of like a security measure to prevent applications from interfering with each other's data or code.
Precisely. But security isolation is just one part of the equation. Borg also implements performance isolation using something called C groups or control groups.
C groups, I'm not familiar with those. What do they do?
So A groups are essentially resource containers that are managed by the Linux kernel. Think of them as virtual boundaries that limit how much CPU, memory, and disk I/O each application can use.
So even if you have a resource-hungry application running alongside a more lightweight one, they won't step on each other's toes.
Exactly. C groups ensure that each application gets its fair share of resources, preventing any single application from hogging the system and slowing down others.
It's like having a referee on the field, making sure everyone plays by the rules and nobody gets an unfair advantage.
That's a great analogy. And to further refine performance management, Borg categorizes applications into different classes based on their needs. For example, there are latency-sensitive applications, like Google Search, that need to respond very quickly to user requests.
So these latency-sensitive applications get special treatment to ensure they have the resources they need to deliver those snappy responses.
Absolutely. Borg prioritizes these applications and can even throttle back less critical applications if necessary to ensure that those latency-sensitive tasks have the resources they need to respond quickly.
So it's like giving them VIP access to the resources, ensuring they always get priority service.
Precisely. It's all about making sure the most critical applications have what they need to function smoothly, even when resources are tight.
Borg's approach to resource management and isolation is incredibly impressive. It's a delicate balancing act, but it seems to handle it with grace. And all of this is happening behind the scenes, invisibly to the end user, right?
That's the beauty of it. Users don't need to worry about the intricacies of resource allocation or isolation. They just submit their jobs, and Borg takes care of the rest, ensuring that their applications run smoothly and efficiently.
So it's like having a personal assistant for your computations, handling all the complex details so you can focus on what matters most.
A very capable and efficient assistant indeed. Welcome back to our deep dive into Borg.
We've been exploring the inner workings of this incredible system, and it's clear that efficiency is really at the heart of everything Borg does.
Absolutely. Google's infrastructure is massive, so squeezing every ounce of performance out of their hardware is essential.
And one of the key ways Borg achieves this is through a concept that might seem a little counterintuitive at first: sharing.
You might think that keeping different types of jobs separate would be more efficient, but Borg actually runs a mix of production and non-production jobs on the same machines.
So those mission-critical tasks are running alongside less urgent ones. that sounds kind of risky.
It's not as risky as it sounds. Remember, production jobs often reserve resources to handle those occasional traffic spikes.
Right, they need to be ready for anything.
Exactly. But most of the time, they don't actually UAC all those reserved resources. Borg recognizes this and cleverly reclaims that unused capacity, allowing lower priority, non-production tasks to run in the meantime.
So it's like having a standby lane for those less urgent computations, ready to take advantage of any open slots.
Precisely. And this approach has a significant impact on overall efficiency. Google's own research, using their cluster trace data, showed that mixing these workloads actually reduces the total number of machines needed.
So it's not just about utilizing existing resources better, it's about needing fewer resources in the first place.
Exactly. It's a win-win. Production tasks get the resources that they need when they need them, and non-production tasks get to piggyback on the available capacity, maximizing the use of every machine in the cluster.
This sharing concept is brilliant. But I'm wondering, how does Borg actually know how much resources to reclaim? It must involve some serious resource monitoring magic.
It does. Borg continuously monitors each task's resource usage and uses a pretty clever mechanism called resource estimation to determine how much each task is actually using and predict its future needs.
So it's not just looking at current usage, it's anticipating future demands as well.
Precisely. Based on this analysis, Borg dynamically adjusts each task's reservation, which is essentially an estimate of its future resource requirements.
So if a task consistently uses less than its reservation, Borg can reclaim the surplus and offer it to other tasks.
Exactly. And if a task suddenly needs more resources, its reservation is quickly adjusted to meet the demand. It's like dynamic downsizing for your computations, constantly optimizing resource allocation based on real-time needs.
It's amazing how Borg can juggle all these competing demands and adjust resources on the fly.
It does all this without adding significant overhead to the system. The Borg master calculates these reservations every few seconds, but the communication of those changes to the Borglet, the software running on each machine, happens asynchronously.
So these updates don't disrupt the flow of operations.
Exactly. It's a testament to the careful engineering behind Borg's design.
We talked earlier about how Borg doesn't use fixed-size resource buckets. It allows users to request exactly what they need.
Yes, the level of granularity in Borg's resource allocation is pretty remarkable. You can request CPU in units of millicores and memory in bytes.
That's incredible. It means applications can be tailored to their specific needs, eliminating the waste that comes with fixed-size resource blocks.
Exactly. It's like being able to order ingredients for a recipe by the gram, instead of being forced to buy prepackaged boxes. You get exactly what you need, minimizing waste and cost.
This granular control, combined with resource reclamation and sharing, clearly plays a huge role in Borg's overall efficiency.
It's one of the key differentiators between Borg and many other cluster management systems, and it's a big part of why Google can run its infrastructure so efficiently.
All right, I'm convinced that Borg is a master of efficiency. But let's not forget about the challenges of running all these diverse applications side by side on the same machines.
You're right, it's not enough to just share resources. You need to make sure those applications don't interfere with each other.
Exactly. How does Borg prevent one application from, hogging resources or causing problems for others?
Borg takes a multi-layered approach to isolation, ensuring that applications can't interfere with each other's performance or security. Think of it as a system of checks and balances to ensure fair play and prevent any application from becoming a disruptive, noisy neighbor.
That makes sense.
Yeah.
So what are some of the specific techniques Borg uses to achieve this isolation?
Well, it starts with security isolation. Borg uses a mechanism called root jails to restrict each application to its own designated space.
Oh, I remember reading about root jails. They're like virtual sandboxes that prevent applications from accessing each other's files or messing with each other's environments, right?
Precisely. Each application runs in its own secure little world, unable to snoop around or interfere with other applications.
So it's like giving each application its own private office, complete with soundproof walls and locked filing cabinets.
Exactly. It ensures that applications can't tamper with each other's data or code, maintaining security and stability across the cluster.
That's reassuring. But security is only one part of the equation. What about performance isolation? How does Borg prevent one application from hogging all the resources and slowing down others?
That's where free groups come into play. Remember those resource containers we talked about earlier?
Right, the ones that allow Borg to set limits on CPU, memory, and disk I/O for each task.
Exactly. C groups act as virtual referees, ensuring that each application gets its fair share of resources and preventing any single application from monopolizing the system.
So even if you have a resource-intensive application running alongside a more lightweight one, they won't step on each other's toes.
Precisely. C groups maintain a level playing field, preventing resource contention and ensuring that all applications can run smoothly.
This system of isolation is impressive. It's like Borg has created a perfectly balanced ecosystem where diverse applications can coexist harmoniously.
It's a testament to the level of thought and engineering that has gone into Borg's design, and it doesn't stop there.
There's more.
Borg also uses application classes to further refine performance management. Remember those latency-sensitive applications we discussed earlier?
The ones that need to respond quickly to user requests, like Google Search.
Exactly. Borg recognizes these applications and prioritizes their access to resources, even going as far as throttling back less critical applications if necessary to ensure those latency-sensitive tasks get what they need.
It's like giving them VIP access to the resource buffet, ensuring they always get first dibs on the best dishes.
Precisely. It's all about ensuring that those critical applications, the ones that users rely on the most, have the resources they need to function smoothly, even when the system is under heavy load.
This all sounds incredibly complex, yet Borg manages to handle it all with grace and efficiency. And all of this is happening behind the scenes, invisible to the end user, right?
That's the beauty of it. Users don't need to worry about the intricacies of resource allocation, isolation, or performance management. They just submit their jobs, and Borg takes care of the rest, ensuring that their applications run smoothly and efficiently.
It's like having a personal assistant for your computations, handling all the complex details so you can focus on what matters most, building and running your applications.
A very capable and efficient assistant indeed. Borg is truly a marvel of modern engineering.
Welcome back to the Deep Dive. We've been uncovering the secrets of Borg, Google's cluster management system, and I have to say, the more we learn, the more impressed I am. It's not just about the efficiency and scale, it's about building a system that's fundamentally robust and adaptable.
You know, it really is a testament to the foresight of the engineers who designed Borg. They weren't just solving for today's problems, they were anticipating future challenges and building a system that could evolve to meet them.
And one of the most remarkable things about Borg is its lasting legacy. It's not just an internal Google project anymore. Its influence extends far beyond the walls of their data centers. It's shaping the landscape of cloud computing as we know it.
Absolutely. Borg's DNA can be seen in Kubernetes, which has become, it's like the industry standard for container orchestration. It's really fascinating to think that the principles and lessons learned from this internal Google project are now empowering organizations of all sizes to build and deploy cloud-native applications.
It's a perfect example of how innovation can flow from within a large organization and benefit the wider tech community. So let's talk about that connection between Borg and Kubernetes. How exactly did Borg influence the development of this open source powerhouse?
Well, a lot of Kubernetes core concepts are directly inspired by Borg. For example, the idea of declarative resource management, where you just describe what you want your application to look like and let the system figure out how to achieve it. That's a core principle that Kubernetes inherited from Borg.
So it's about simplifying the user experience, abstracting away those complexities of resource allocation, and allowing developers to really focus on what they do best, building great applications.
Exactly. And another key concept is the use of pods as the basic unit of deployment in Kubernetes. This idea of grouping containers that perform related functions together into a single manageable unit. That came straight from Borg.
It makes sense. You want to manage those related containers as a cohesive whole rather than as individual pieces that are scattered across the system.
Precisely. And then there's that emphasis on automated scaling and self-healing capabilities, ensuring that applications can adapt to changing demands and recover from failures automatically. These are all principles that were first implemented and refined in Borg.
It's like Kubernetes inherited Borg's best qualities, right? The efficiency, scalability, resilience. It took those core principles and made them accessible to a wider audience.
That's a great way to put it. Kubernetes took the essence of Borg and adapted it for a more general-purpose audience, stripping away some of the Google-specific intricacies, and providing a more flexible and extensible platform.
But it wasn't just about replicating Borg's successes, right? The Kubernetes team also learned from some of Borg's limitations and made deliberate design choices to address them. Can you give us some examples of that?
Sure. For instance, one of the things, we learned from Borg is that having a single monolithic job abstraction can become a bottleneck when you're dealing with complex applications that consist of multiple interconnected services.
Yeah, it works well for simpler scenarios, but as applications grow in complexity, you need more flexibility and granularity in how you manage them.
Exactly. So Kubernetes introduced the concept of services and labels, which allow developers to group and manage pods in a more sophisticated way, defining relationships between different parts of the application and managing them as a cohesive unit.
So it's like providing a more nuanced set of tools for orchestrating those complex, multi-layered applications.
Precisely. And another area where Kubernetes diverged from Borg is in its approach to networking. Borg's approach of having one IP address per machine, while efficient for Google's internal network, it proved to be limiting for external users who needed more flexibility in how their applications interacted with the outside world.
So Kubernetes took a different route, right? Assigning each pod its own unique IP address, which opened up a whole world of possibilities for integrating with external networks and services.
Exactly. That change made Kubernetes much more adaptable to different networking environments and use cases, greatly expanding its potential and appeal.
These are just a few examples of how the lessons learned from Borg, both its successes and limitations, they directly influenced the design and evolution of Kubernetes. It's a remarkable story of innovation, adaptation, and the power of open source.
It really is. It's a testament to the willingness of the Kubernetes team to learn from past experiences and build a system that addresses the real-world needs of developers and organizations.
And the impact of Kubernetes has been, well, I mean, it's been undeniable. It has become like the de facto standard for container orchestration, driving the adoption of cloud-native technologies across industries, from small startups to like Fortune 500 companies.
Yeah, it's incredible to think that a system that was born out of Google's own internal needs is now powering applications for such a diverse range of organizations, helping them to build and deploy software with incredible speed and agility.
It's a testament to the enduring value of good design principles, the power of open source collaboration, and the ripple effect that innovation can have when it's shared with the world.
Absolutely, and it all goes back to Borg. This pioneering system that pushed the boundaries of what's possible in cluster management and paved the way for this whole cloud-native revolution we're seeing today.
Borg's legacy lives on in Kubernetes, democratizing access to Google-scale technologies and empowering anyone with an idea to build and deploy applications that can reach global audience.
And the story doesn't end there. The Kubernetes ecosystem is thriving, constantly evolving, with new features and capabilities being added all the time. It's an exciting time to be involved in the world of cloud-native development, and Borg's influence continues to shape its trajectory.
Well said. And on that note, I think it's time to wrap up our deep dive into Borg, Google's secret weapon for conquering the world of data. We've journeyed through its intricate workings, explored its remarkable efficiency, and traced its impact on the evolution of cloud computing. It's a story of innovation, adaptation, and the power of shared knowledge.
It has been a fascinating exploration, uncovering the layers of complexity and ingenuity that make Borg such a remarkable system. And it's inspiring to see how its legacy lives on, empowering developers and organizations to push the boundaries of what's possible in the world of software.
So, as we conclude our deep dive, we encourage you to explore Kubernetes, delve into its capabilities, and imagine the possibilities of building Google-scale infrastructure for your own projects. Who knows? Maybe your next big idea will be powered by the principles and lessons learned from Borg, this groundbreaking system that continues to shape the future of technology.
And that's a wrap on this deep dive into Borg, Google's secret weapon for conquering the world of data. Until next time, keep on learning, keep on exploring, and keep on innovating.